Hello, I'm Ryan Hayden and I'm a soil scientist at Ohio State ATI. Today what we're going to be doing is a lab activity focused on grid soil sampling. And that process starts out in the field. So we're going to head out to a hayfield and we're going to collect soil samples using a systematic grid sampling pattern. We're going to capture that data with specialized software that allows us to put a latitude and longitude on those soil samples. And then we take that information and back here in the computer lab, we can then develop prescription maps that are useful to farmers who may want to apply lime or fertilizers on a variable rate basis. They might apply a little more fertilizer or lime to one part of the field that needs it and a little less to parts of the field that don't. And this has a lot of value for farmers and the environment. Farmers are looking to save a bit of money by only applying fertilizer where it's needed, and they're looking to reduce their environmental footprint by not over applying nutrients that can subsequently be lost to the environment and affect water quality. So the goal of today's lab is to provide you guys with the skills to be able to collect grid soil samples and then convert the information from the soil that's analyzed from those samples into prescription maps. So that's the goal for today. And now let's head out to the field and see what's involved in this process. We're using the Cirrus SST app to collect soil samples on a consistent grid. So we call this grid soil sampling. And you'll notice here we're in the truck right on the edge of a hayfield, and we've got our hayfield marked out on our iPad here. And that little dot there is where we're located. We are connected to this through Bluetooth to a Garmin GPS unit, which is telling us where we are. And what we're going to be doing here is overlaying a grid. And so to do that, I'll hit this little plus sign and it gives me a drop-down menu, and I select grid soil sampling, and you'll see that the grid is now displayed. I can adjust that grid to make sure that it lines up with the edge of my field. And so now we've got 12 1-acre grid cells on the screen that we're going to be collecting our samples. We're going to set our grid, and you see those little round circles is where we're going to be trying to drive to and collect our soil samples. In order to do that, we need to set our navigation route. So I'm going to drag my finger through these circles, and that's going to essentially be the route that we drive to collect those samples. So once I've done that, I can set the route by hitting this button there. And now our goal is to drive to the center of that grid cell. And so it says we need to drive straight 33 feet. So that's what we're going to do. And Jordan here is going to be our navigant for the remainder here. So Jordan, when we get to the center of that circle, let me know, and then you can hit that green drop point button, and it is recording the latitude and longitude of that spot. And at that point, we'll hop out of the truck and we'll collect our soil sample. All right, fellas. So next step here is we've got our 12 buckets. Each bucket corresponds to an individual grid cell. And since we're located in the spot where we're supposed to sample, I'm going to give the honors to you over here to basically pull the soil sample anywhere in this 10-foot vicinity, and we're trying to sample down to about 8 inches. So just give it a good push. All right, and then just twist it a little bit as you come up, and you should have, that is a very nice sample there. So our goal here is we're going to be adding it to our composite bucket where we have other samples from the same spot, and usually it's a bit easier to remove the core with our screwdriver here. So why don't we just stick this right in there, and I will just pop out that core. Usually, it comes out pretty nice down, and then down at the bottom it sometimes can get a little bit challenging because we've got some moist soil here. So that's why our screwdriver comes in handy to knock that out. And that is the final product there. So this is bucket 1 from grid cell 1. On to number 2. All right, so now that we've got all 12 of our samples collected for all 12 of the soil grids, we will take these samples, let them dry out a little bit, and then send them off to the lab for analysis. So that's really the first step in grid sampling, is to collect a grid, have it georeferenced with the Latin long. Once you've got your samples, then you can send them off to the lab. While many folks still soil sample with a hand probe, one of the ways that the industry is moving forward and trying to make this fairly labor-intensive process of collecting soil samples more efficient is through the introduction of soil sampling technology. So what we've got here is a hydraulic soil sampler. This particular model is made by Wintex, and the idea is that we can use hydraulic power starting from a Honda motor to power the hydraulics to push a probe, very similar to what we were pushing by hand, down into the ground, and it will collect that core and deposit that core into this cup. And so the real value of this is that we can now collect many more samples a lot more quickly. And it takes a lot of the back-breaking element of soil sampling out of the equation. So for those that are covering lots of acres and having to grid sample, as their career, this is really a great asset to their efforts. All right, so now I'm gonna turn on the hydraulic pump so we can get started. All right, so we've now got our hydraulic lines powered, and for this particular model, you actually need to have the engine of the UTV on and running. And I like to say that this particular model is farmer-proof because you have to have the brake engaged, and you have to have your other foot on a pedal to engage the soil probe. And then what we can do is we hit this button here, and it rotates and presses down and pulls a core. And when it gets to the bottom, it pops up and deposits that core into this cup. So I've got this set basically to take 6-inch samples consistently. It can also be set to go from a range of anywhere from 0 to 12 inches.
Hello, I'm John Witter. I'm an agricultural engineer at Ohio State ATI. I'm here to talk about the process of taking our soils location information along with the lab data and turning that into a prescription map the producer can use to apply lime or fertilizers. This process can hopefully reduce input costs for the producer or increase their yields. It certainly helps reduce the risk of runoff of nutrients, so it's a sound environmental practice. Let's take a look at the farm management software we'll use to make a prescription map. So, at this point we've pulled soil samples and recorded their locations in our tablet that was connected to GPS. The samples were numbered to correspond with each site and then sent off to a certified lab for analysis. The lab results were emailed, and now it's our job to merge the location data with the lab results to determine the spatial variability of nutrients and other soil characteristics, like soil pH, throughout the field. Once this variability is known, we can then use our farm management software, here we're using Trimble Ag software, to make a variable rate prescription to optimize the application of crop inputs. In other words, we'll utilize the data to make agronomic decisions about the placement of inputs, like fertilizer, lime, seed, or pesticides, to various areas or zones within a field. Depending on where you're at in Ohio, there can be a huge amount of variability in yield potential throughout a field, or other places there may be very little variation. Where there is substantial variation, it is often due to factors such as soil texture or drainage, or perhaps part of a field have been managed differently over the years. As a result, the optimal amount of inputs to maximize profitability varies throughout a field. Let's take a look at phosphorus levels in the fields we've sampled. As you can see, there's a great deal of variation in phosphorus levels throughout the field. In particular, you can see the high levels of phosphorus that actually exceed agronomic needs around the entrances to this field at the north and south ends. What has most likely happened here is that livestock manures are spread on these fields nearly every year, as they are near the dairy and beef cattle facilities, and oftentimes the majority of it is spread as the operator enters the field from the road or driveway. You can see that the areas further away from the entrances are much lower in phosphorus and actually considered deficient for crop production. So our goal is to apply fertilizer only where it is needed, in the amounts that are needed. Our guide to determine the amount of phosphorus that should be applied is the Tri-State fertilizer recommendations. Our first step in the process is to select the type of fertilizer that will be used. Let's use diammonium phosphate, or DAP in this example. First, we need to create the supply in the farm management software and include information such as the percentage nitrogen, phosphorus, or potassium it contains, as well as the cost per ton, which can be used for accounting purposes to document and track production costs. Our next step is to write a simple formula derived from the Tri-State fertilizer recommendation that tells us how much P to apply based on the soil test levels and our corn yield goal. For example, if we have 30 parts per million P for the Malick 3 soil test and a realistic yield goal of 170 bushels per acre, then we should apply 65 pounds of P2O5. For additional information on deriving these formulas from the Tri-State Fertilizer Guidelines, you should contact your local extension agent or state university. Using these formulas, we now have an application map based on the Tri-State Fertilizer recommendations. You can see that the areas that were high in phosphorus receive no fertilizer, whereas the deficient areas are receiving the highest application rates. Hopefully, the steps we described here will let producers reduce inputs where they're not needed and sustain current yield levels, increase inputs in zones within a field where additional investment leads to higher yields and improves overall profitability, and importantly, reduce environmental risks of nutrient losses to our critically important streams and rivers that so many Ohioans depend upon for their drinking water, livelihoods, and recreation.
We hope you've enjoyed learning about the process of grid soil sampling and prescription mapping. I, for one, am really excited about this technology and feel that the next generation of farmers will increasingly use this technology to implement precision farming technologies. Thank you very much for joining us.